Well, good afternoon. Welcome back after the break. I was just watching the logo, thinking that we should have a flipper sanitizer SAO. Yeah, so this next session is going to be talking about the various wares for the Rockling, the swag bags, and the party buttons. So this is the collection of hardware that we've been playing with throughout developing this project. So we can see the old last year's swag badge. We've got the new swag badge. We've got various Rockling prototypes in production, and there's no party button there. And so for those who are new to FPGAs, I'm going to sort of dive in. There's lots of terminology jargon, but don't let that put you off playing with your Rockling. But at first they'll appear like a RISC-V processor just running C code. All the I2C peripherals are controlled by C, and all the CPU and the peripherals appear on a memory map bus, which you can just interact with directly from your laptop. So you can basically peek and poke and send commands to see what's going on. And as you gain more confidence, you can dive in deeper into the world of the FPGA tools and right down to the individual gates. So let's go. So we use software to control hardware, and typically that hardware's got specific functions. It's either a CPU or a GPU. It could be some sort of peripheral like an accelerometer, and it's pretty hard for most of us to create or change these ICs. You need to be a large corporation, and these ICs may have a small number of gates, maybe a dozen or so, up to many billions of gates. And most of us we work in software. Throughout the OHMC projects, when we're doing embedded devices, we use firmware, which is just a form of software that just takes a little bit longer to write, a little bit longer to flash, and a little bit harder to change. So this year with the FPGAs, we're going to be playing with gateware, and so I'm just going to chat a little bit about what the gateware is. So FPGAs, which stands for Field Programmable Gate Array, is a sort of IC that's is programmable. You can change its function, and it consists of quite a few different parts. The first three of these main things are what are called the lookup tables, which allows you to do what's called combinational logic. This is sort of the ands and ors and not gates, the logic gates, and what a lookup table allows you to do is to have a number of inputs and typically a single output. And for any combination of inputs, you can define what that output is, and it might use RAM to just create that lookup table. But what combination logic gates can't do is that they don't allow you to. They're time independent, so it doesn't matter what any previous states are. They'll always produce the same result. So if you want to basically have a maintained state and have different results over time, use flip-flops. This is for doing sequential logic, and you can maintain previous state, and as you have new inputs, your output can depend upon a previous state. And the other part we've got in FPGA is what's called carry logic. So if you've got a number of cells, if you want to make like a shift register or something like that, you can chain the output from one cell to the next. And so these logic cells are a combination of a lookup table, flip-flop, and the carry logic. And on the FPGA that we're using in the Rockling, you have about 5,000 of those lookup tables. The other thing an FPGA has is the routing between logic cells. You also have clocks, which provide clock signals out to all these cells to synchronize them. And in the case of the FPGA that's chosen, there's also a fair amount of memory. You've got 128 kilobytes of RAM. The other thing FPGAs provide, so you don't have to do everything yourself in using your own the logic gates, is you can get specialized circuits for doing I2C or SPI buses, and including digital signal processors for doing fast arithmetic. And so what the gateware is, it's the definition language that allows you to describe your FPGA and then program it. So this is what's called the gateware. So this is a diagram from the Lattice documentation, and you can see a logic cell has these components. The lookup table, the output lookup table goes to the flip-flop, and also your carry logic. And so you can see on the left-hand side, if you had 8 cells in a row, you might create a shift register by having the carry logic transfer the output from one cell to the next. So that's sort of a quick overview of what goes on inside an FPGA. Should have kept track of time. So if you want to basically define what goes on an FPGA and then flash or program the FPGA, there's open source tool chains now, like for example SymbiFlow, and so you start off with a module description, so it's like module.v in a hardware description language like Verilog, and it describes all the combination logic and the sequential logic and so on, and how you want to use the different hard blocks, and use a program called Yosis, which turns that high-level design into the actual logic gates. Then there's a program called NextPNR, which then places those logic gates into the various available resources of the FPGA, and then it routes all those logic cells together. And then you need to create what's called a bit stream, which is a configuration that's usually specific to the particular FPGA you've chosen, and then finally the FPGA we've chosen has a bootloader which allows it to appear as a USB device, and there's a standard tool called DFU util, which writes that bit stream to the Rockling FPGA. So that's the general process. So why have we chosen to use FPGAs, and why are other people excited about them, given that most of the time we can just use CPUs and GPUs and other sorts of peripherals, and don't even need to touch an FPGA? Well, if you're using something like an Arduino processor like an Atmega 328, sometimes you run out of PWMs, or you just like to have another I2C bus or something like that, and you don't have much choice except to just choose another chip. Or it'd be really nice to if there's an operation do really a lot, and it's just slow to do in the instruction set, it should be really nice to be able to add another instruction, or if you want to add a FPGA HDMI output. And these are the sort of things you can do quite easily with an FPGA. And also, if you compare the performance of these small microcontrollers, they all have a very similar price, sort of like $5 for the up 5K versus a couple of dollars for an Atmega 328, or a bit more for an STM32. Because the FPGA we've chosen has digital single processors, you can, if you have 8 of those doing 16-bit multipliers at 48 megahertz, that's a lot more horsepower than you get out of an Atmega. So you've got these sort of flexibility advantages. And whilst we're playing at sort of the very low end of the spectrum in terms of number of lookup tables, so it's only about 5,000 in the up 5K that we've chosen. That still allows you to do quite a bit. So comparing it to the original 6502 microprocessor, which had about 3,500 transistors, there's more than enough lookup tables to replicate the functionality of a 6502. And so you can effectively put like a whole Apple II inside this little up 5K, or even a 32-bit RISC processor. But just in comparison, at the other end of the spectrum, a modern processor like you'd find in your Mac, that's about nearly 60 billion transistors in that. Similarly, with a top-end GPU from AMD or even Xilinx, that's also around 60 billion transistors. But if you look at what you can get from an FPGA, it's nearly 100 billion transistors. So even though we're only playing with a small number of gates in the Rockling, the same techniques would allow you to acquire a very, very large FPGA, and you could write your own modules to utilize all those transistors for a very, very custom job. So you can apply the hardware resources, your transistors, to exactly what you need, and not waste them on anything you don't need. So why should we take interest in FPGAs now, given they've been out since about 1985, so it's several decades? And one of the main reasons is a lot of open source developers, like people like Tim Ansel, have been pushing very hard to develop out open source tool chains, and so it's becoming much easier to use now. So for decades, the definition language like Verilog and VHDL were roughly like the same sort of, I guess, abstraction as writing C code. And these were tied very close to proprietary tools. They were very slow, sometimes with steep learning curves, and that was fine if you're working in FPGA, day in, day out as your main job. But if you just want to, have a bit of a play or occasionally use it, so it wasn't very attractive. These days, you can use high-level languages, Python in particular, but also Scala and others to define your FPGA logic using a higher level language, so you're not so down at the low level of the logic gates. And then there's also additional software like LiteX, which allows you to deal with whole components. So like a whole 32-bit processor or a whole bus. And you can use this to connect together modular components, so your CPU, your controls, and so on, into a quite high-level design. It's much easier to use. And there's diagnostics tools like LightScope, which allows you to have a logic analyzer, so it's become much more approachable. And if you also find there's plenty of existing Verilog modules or VHDL in GitHub or OpenCores, you can still integrate those into your design. And so you can now pretty much work entirely in open source tool chains and for your FPGA. And often these tools do synthesis much faster than the vendor tools. So additional reasons why perhaps you're interested is it's even though you may not need to use the FPGA very often, it's still very capable thing to have to know how to do, and it's also just fun if you're into nostalgic hardware, or you want to do like video games or do your own CPU design. It's something you can very easily play with FPGAs. And so why not have the best of both worlds? Use ASIC CPUs when you need to, and combine them with FPGAs if that helps. So in terms of getting started, the up 5K is it's fairly inexpensive. It offers a good range of capability, and so Tim Ansel and his colleagues produced the FOMU a few years ago, back in I think 2019. There's also things like the Icebreaker, and now this year we've produced the Rockling. Tim's workshop's a great place to get started, and also hopefully the rest of this presentation will give some more insights. So the inspiration for the Rockling was that last year when we did the swag badge, we didn't spend as much time on SAOs as we would have liked. We were hoping to encourage more people to produce their own simple boards to add on to the swag badge. And so we thought it'd be nice to try and create the most interesting SAO we could. Some people have been chatting for a while about doing an FPGA, and we were long overdue to do a FPGA project. And so we start off with some foamers that Tim had provided, and saw that we were able to create the bootloader for it. And so John 3D printed a rig so we could flash our foamers with FOBoot, and that worked, so that was good. And Andy Kitchen was also working with FPGAs as part of his work, and so we just sort of had all the right people. Bob had some time to do the design, and we're thinking, well, what could we do if we try to design our own FPGA board, and playing with audio was something we hadn't done before, so that seemed a natural thing to do with the 8 DSPs, and then to say, well, what we're going to do with audio processing, we thought, well, let's make a musical instrument, and I think it was Andy who had the idea of making a Theremin. So that's how the Rockling came about. So we start off with some FOMUs, and if you want to get they run flash, so we had to basically flash the SPI module, flash memory, and so we did that initially by soldering some wires on, which are very, very fine pitch, and we managed to do that. Well, it was a bit cumbersome, and so after that, John 3D printed the a little test jig, so we basically just placed the FOMU in the test jig and just flash it on a Raspberry Pi, so that worked. And then if you wanted to actually play with the FOMU, like there was these four tiny pads for GPIOs, so we attached wires to that, and the reset button, that was a bit also a bit cumbersome, but that sort of gave us some confidence that we could build the tool chains and get going. And even though there's only 4 pins on a foamer, you can still create an I2C bus, an SPI bus, or even drive FPGA. So even though it's only a very tiny board, it's you can still have some fun with it. And then from there, we Bob with Andrew's Nielsen's layout and Bob's electronics design, we produced the first prototype, and it was a challenge getting that up, because unlike when you put a CPU down on a board, if it usually has an internal clock, or if you apply a clock signal, it pretty much usually works right away, or it's easy to diagnose. One of our first problems was we mistakenly chose the wrong internal global system clock pin to use, and just nothing worked. And it was not immediately obvious how to what the problem was, but we eventually figured it out and managed to get the FPGA clocking, and we were able to flash it and flash an LED. So that was encouraging. And then one of the key things we want to do is make it easier to flash and interact with the chip. So we basically put as a header on the Rockling, which gives us both I2C and SPI. So it would make it easy for us to reflash the bootloader, and also to interact with the device over a SAO from the swag badge. So you can see that's there. Once the prototype was done and we'd pretty much proven out that the fundamental design worked, we then went on to produce the production boards. And it was a pretty exciting day when they first came back, because we were able to test Andrew Nielsen's tiling and see that they truly did tile the plane, and we could make some pretty patterns with them. So getting down to some details. So this is the sort of a block diagram what's going on inside the Rockling. So at the heart of it is the FPGA, and towards the front of the fish, the fish head, where the fish eye is, that's the analog front end for a Theremin. So a Theremin has 2 inputs, a volume and a pitch antenna. So you basically move one hand for volume, another hand for pitch. And I think during Bob's talk later today, he'll talk about some antenna design. But Bob took the design from Open Theremin, and so basically just translate that onto the board. And usually has an Arduino at mega chip rather than FPGA. But what we did was basically took the volume and pitch that came from the front end, which should be roughly 500 kilohertz, and it just varies slightly by maybe 20 or 30 kilohertz based on your hand position, and have that come into the FPGA. On so the Rockling has both an I2C bus for interaction with the swag badge, and an internal I2C bus for talking to the DAC, which provides 2 output voltages, one to act as a bias for the volume, and another to act as a bias for the pitch. And the other thing that's on the bus is the audio codec. So the FPGA is I2C to control the DAC and codec, and downstream from the audio codec is the amplifier. So the idea is that with the FPGA, with the DSPs, we'll be able to synthesize, hopefully, some sophisticated sounds to give that sort of classic Theremin noise, and then over the I2C bus would send that data to the audio codec, out to the amplifier, then to either a headphone jack or speakers. And you can also see at the top the flash memory is on the SPI bus, so that allows the swag badge to initially flash the bootloader onto the flash memory. So when the FPGA is powered up, it'll load its bit stream from the flash memory. The final piece in that diagram is USB. So there's GPIO pins from the FPGA go directly to a USB connector, and how that works is the FPGA has a RISC-V processor, which has a USB stack written in C. And so when you power the FPGA up, it appears as a DFU device, which is a standard way of loading firmware onto devices over USB. So just to recap, we'll provide the Rockling with Fobo already flashed on it. But if for any reason we need to change or reflash it, then the swag badge can use SPI to reflash the flash memory on the Rockling. The main primary way of interacting between the swag badge and the FPGA will be via the SAO I2C bus, and allows the swag badge to provide a user interface or networking for the Rockling. The FPGA has a little bit of gateway that measures counts the volume and pitch input frequency, and then uses we've got a soft I2C bus controller for controlling the DAC and the audio codec, and also there's an I2S module as well. As mentioned, the Rockling, when you plug into USB, the Rockling appears as a DFU device, and you use DFU util to list it, and then also to flash code. And there's also what's called the wishbone bus. So all the peripherals on the Rockling appear on this 32-bit bus, and you can just use a laptop wishbone command on your laptop to interact with all those peripherals. So the FOMU normally comes with a RISC-V soft core that's quite capable, but it also consumes quite a lot of resources. So Andy was able to find a smaller implementation of RISC-V called Femto, I think Femto RISC, I think it was, which didn't use quite as many logic cells, so we were running out of room. So during the process of going into production, you can see there's lots of bodge wires on the prototypes, as we had to use a different pin for the system clock, and also wires there for testing out things like the USB and so on. And then as we bring each board, you can see there's like a checklist of what things were working. So we had to make sure the bootloader worked and appeared over USB, that the RGB LED was working, just as this big checklist, which we're still going through now for each of the boards. Right, so looking at the whole project, the project as a whole, so the swag badge, the party button, and the Rockling. This is a bit of an overview of how these all hang together. So the party button can operate standalone. I think as John showed earlier, you can just put this little base board that has the battery, and it just basically short circuits the button to the MOSFET. So you just press the button and the LEDs go on. But if you take that little standalone adapter off, you can connect the party button up as a SAO, which then means the GPIO input from the button or the output to the MOSFET can then be controlled by the SP32 on one of the SAO connectors. And similarly, you can connect the Rockling up to one of the SAOs. So we've got SAO 1 has got not just I2C but also the SPI bus. So if you you can use that SAO connector for flashing the Rockling from the swag badge if you need to. Otherwise, we'd normally put it on a SAO 3 on the right hand side of the Rockling the swag badge, and that's provides an I2C bus for interacting with the FPGA, and also the GPIO is used for resetting the FPGA and listening to the configuration done pin. And then finally, on the Rockling also has the USB connector for doing development from your laptop. So the idea is the swag badge is for SAOs. The swag badge provides a user interface, and you can also provide additional program control monitoring and also the networking. And we wanted to have the party button SAO as a server. We always like to give people the opportunity to learn to solder, and also get a simple introduction to making SAOs, where there's just a button in and a MOSFET out. And some of the simple ideas is to basically allow the swag badge to provide more complex behavior than just a button controlling LEDs, or you maybe do some networking and connect a couple of party buttons up together. So finally, just talking about the Rockling, the primary way we intend the Rockling to be used with the swag badges are using the SAO I2C bus, where the ESP32 is the I2C controller and the Rockling is the peripheral. And we've got the two pins for GPIO pins for resetting and checking the configurations done. And then we've also got the other header for the SPO pins for flashing. And then on your laptop, you'd use we'll provide instructions on how to use SymbiFlow and set up the tool chain for creating an FPGA bit stream. You simply just type make, and it basically runs all the Python code and LaTeX for for creating the bit stream, and you then just use the DFU usual just to flash that onto the FPGA.
5 minutes.
Yeah, still got 5 minutes, so that's a quick run through. So, okay, what sort of questions do we have?
Okay.
Did any of that make sense?
I'm just jumping back in to pass through some questions that came in the chat. So, the first question, and other people can chime in with this as well, is do you have any real-world problems for when you'd use an FPGA versus a traditional MCU, and why?
In a situation where we have lots of parallel inputs, we would need to do signal processing as a classic use for an FPGA. So it's one thing to look after a small number of inputs through a microcontroller, but if you had like 100 signals so you need to look at simultaneously, then an FPGA would be ideal for that. Another situation people are looking at is with CMOS transistors. Whenever you change state, that consumes power. If the transistor is not switching, it doesn't use any power. So with an FPGA, you can minimize the number of transistors to just what you need. So for people who are playing with neural networks where they only need single bit, they don't need 8-bit or full 32-bit numbers. Applying an FPGA to small neural networks to save power is another option.
Okay. Next question is, will FPGA save us from the component shortage apocalypse and replace hard-to-buy IP with an FPGA?
well, perhaps. As a bit of an aside, there's companies like Apple and I think also Tesla doing the same thing, where they control their complete tech stack. And so in contrast to other car manufacturers, when there's a chip shortage, Tesla was able to get different chips and just rewrite their software stack to use those different chips. Whereas if other companies like GM and so on, who were dependent upon other third parties, they were stuffed. If they couldn't get the chips they needed, they couldn't change their software. So in a situation where you can control your whole stack, and you can have something like an FPGA, and you can change it to for your needs, then perhaps.
And this is on the the optimistic side of things, where the FPGAs themselves remain available, which is difficult as well.
Yes. But I certainly like the idea that if you've got you basically need a CPU and you've got some other digital logic that to be able to integrate that onto a single chip is a nice thing. And if you do need to make some simple changes, you don't have to go and buy new different say small scale integration chips. You just simply change your FPGA. That's certainly a nice thing. So I think we saw that in the early days of hobbyist PCs, where the first Apples and other things where they maybe used 20 or 30 or 40 chips, and you look at something like an Apple II GS and it was only like 6 chips. And so increasing your integration is always a good thing.
Also, a question specifically about the Rockling is, can we use the Rockling to do stuff even if we don't touch the FPGA at all?
Yes, great question. You can, because the first way you can start to use the Rockling is simply as a RISC-V processor that has the peripherals, the I2C control and peripherals, the DAC and the audio codec, and there's just C code. There's initializing these peripherals, and then sending I2C commands to set the DAC is really easy to use. It's basically one command to set the voltage for one channel. So with 2 commands you can change the voltage on the 2 channels for the front end. The audio codec is a little bit more complex to control. It's still going through that, but it takes a series of I2C commands to set up the inputs, the outputs, the clock rates for the I2C bus. Sorry, the I2S bus and so on. But that is all just C code that we're changing on top of the FPGA.
Okay, and one final question, which I think is a very interesting one. What would it take to expose the FPGA wishbone bus as an external memory device to the ESP host processor, e.g. memory-mapped gateway peripherals?
Okay. Let me think about this a sec. So the wishbone bus allows you to wrap any peripheral as in the FPGA as a on a 32-bit address. And so what we could potentially do is, and I'm really making this up on the fly, is we communicate between the ESP32 as the I2C controller of bus 0 and the FPGA as the peripheral. And so if we had well, actually, we already do have the ability to send wishbone commands that write to the I2C bus. Yeah, I'd say it's potentially possible to use wishbone commands to talk to the I2C bus with the ESP32. So it'll take a little bit of work, but I can see it's possible.
I said that was the final question, but there is actually one more that was in the chat.
Oh, sure.
Unfortunately, we have to answer no. The question was, can we have a performance of the Theremin? And unfortunately, it's not quite at that functional point. There has been validation of various parts of the circuit, but we do not have the complete working system. So things like the oscillators in the analog front end that read from the antennas to measure your hand position and those sorts of things. There's been some testing done of those, and we can see on the oscilloscope that the signal coming out of them makes sense.
Oh, and better than that, we've actually got the FPGA is actually counting the frequency. So there's a couple of diagnostic tools. One allows you to reference let's say again, the ROM and the RAM of the RISC-V CPU is mapped onto the wishbone bus, and so you can actually get the when you compile the C code for the RISC-V, you can actually get the memory map of the various C variables, and so you can actually just on the wishbone bus look at those, and so you can actually see the C code that's the C variable that's actually counting the frequency. So there's that way, and so yes, we've seen that it's correctly counting the Theremin input. What we haven't got fully going is the RISC-V processor on the FPGA seeing the right I2C commands to set up the audio codec, by which we would get sound out.
Yeah, and we're pretty much out of time. We're a minute or two over time now, but there was one question, which is how many times can you reflash these things? And then I think we're going to have to wrap it up.
We're using a standard flash memory module, so you could reflash it, I don't know, thousands of times.
Thousands or tens of thousands.
Yeah, lots there. So not likely to hit that limit anytime soon. Okay. Well, I hope that was useful and made sense. It was all a bit of a rush, but thank you for listening.
Great.
And we're looking forward to getting this in your hands and collaborating on building some stuff.
Yeah, so in a couple of minutes we will be back at 2:40 p.m. Tisham will be talking about open hardware weather radar. So
awesome.
Thank you very much, and we will see you soon.
Yeah, okay, thanks.